Continuing with our discussion of gases and their properties and behaviors, I'm going to take a look at what I sometimes call the ABCD gas laws. Several of these gas laws happen to the discoverers of them. Their names begin with A, B, C, or D. And we're not going to run in alphabetical order. We're more or less going to run in chronological order for their discoveries. Boyle, Robert Boyle, very famous chemist, taught us that the volume of an ideal gas, that's a gas that behaves with, as we discussed earlier, with no interactions other than bouncing off of one another elastically when it hits its container or other molecules, and that have such a small volume compared to the size of their container that we can ignore their volume. And the volume of an ideal gas then varies inversely with pressure. That means that as pressure goes down, volume goes up. Or to put it a different way, as pressure goes up, volume goes down. So if you take a balloon and squeeze it, it's going to get smaller. Or if you put it in an environment where the pressure is much less, that balloon can expand. And so we can write that law a number of different ways mathematically. This law assumes that the system is closed, so no molecules are escaping in or out, and it assumes that the temperature is staying the same. And so the most useful way probably that we can write this is that if we have a closed system at a constant temperature, pressure times volume is constant, so that if we change the pressure of the container by squeezing it or by letting up on it, then the volume change is going to respond in such a way that the product still remains a constant. And there's some problems suggested at the end of this talk that you could try in your textbook. Here's an illustration of Boyle's law. Let's say we have a particular piston set up, and we start to push on this piston. This disc is set up so that it's very, very tight. No molecules can come in or out, but it's greased really, really well, so it can slide up and down easily. And the atmospheric pressure against this disc is 1 atmosphere. That means the pressure inside is 1 atmosphere. But if we push on the piston and double the pressure, the volume gets cut in half. So pressure times volume, 1 times 1, pressure times volume, 2 times a half, both are the same. Pressure times volume is a constant. All right, and this is how it would come out mathematically then if we make a graph of volume versus pressure for a particular closed system. If we have very low pressure on the system, it's going to have a high volume, and as we squeeze it, the volume is going to go down, and we get this exponential looking curve. To get a linear fit, we can plot that same data, plotting volume versus reciprocal of pressure. So this is the exact same data that we have over here, but instead of using pressure on the y-axis, we use 1 over pressure on the y-axis, and that gives us a equation in this form of y equals mx plus b. Volume equals slope times 1 over pressure plus the y-intercept, which in this case is 0. Another one of the ABCD gas laws, Charles' law, states that the volume of an ideal gas is going to vary with temperature. So if we keep pressure the same by using a very flexible container like a loose piston or a balloon, then the hotter we heat up the container, the larger the container is going to get. And we can see this with weather balloons and other kinds of balloons. We heat them up, they expand. So volume over temperature is a constant. And again, maybe the most useful way that we can set this equation up is like this. V1 over T1 equals V2 over T2. The trick in making sure that we get correct mathematical results in this equation is that we cannot use Fahrenheit or Celsius for temperature units. This equation only works if the temperatures are in units of Kelvin, where the lowest possible temperature is absolute 0 and there's no negative temperatures. So if we keep pressure the same and we keep molecules inside the same, but we go from having a half a liter with this very easy to move disk at 200 Kelvin, which is very cold, that's below 0 Celsius and below 0 Fahrenheit, and we heat it up to 400 Kelvin, which is actually very hot. That's hotter than the boiling point of water. That doubles the temperature in Kelvin, so the volume would double. And volume over temperature, you guys can try that out in your calculator. Volume over temperature, you're going to get exactly the same number in both cases. In this case, volume versus temperature gives us a linear graph, and if we do that in Celsius instead of in Kelvin, then we don't get a y-intercept of 0. Look what's happens here. Matter of fact, we're not even going to go down to a y-intercept because it doesn't make sense, because the smallest possible volume you can have is 0. But this is how we discovered that there's the coldest possible temperature. If we figure out this linear equation up here in the areas that are easy for us to set up temperature-wise, 100 degrees, 0 degrees Celsius, which is 32 Fahrenheit, a little bit colder, minus 40, it's when it's very, very cold outside up in Minnesota. That's the temperature inside of the freezer at the grocery store. And we extrapolate that line further down, what we realize is that 0 volume is minus 273 Celsius. Well, that must be the coldest possible temperature. All right, A, B, C, D gas laws. Here's the A gas law. The volume of an ideal gas varies directly with its molecular amount. That means if we keep pressure and temperature the same, the more gas we add, the bigger the container gets. So volume is directly proportional to N. This really works well as an illustration with a balloon. The more air I put into a flexible balloon, the bigger it gets. And so knowing all of these gas laws, the question that comes up, if we have this container and we don't let any gas molecules in or out, and it is at 250 Kelvin, and it's got this much gas in it, and this is the pressure, what's going to happen if we increase the temperature but keep pressure and moles the same? And then what would happen to it if instead we kept the temperature the same but we cut the moles in half? That would make us have less, but cut the pressure in half, and that's going to make it expand. And here's what happens. If we keep everything the same except increase the temperature by 50%, then the gas's volume is going to expand by 50%. But if we keep temperature the same and cut the moles in half, that would bring us down to half the volume. But then we release the pressure and we get double the volume. And so this container has the same volume as this one. All right, here's the all-important gas law that we're going to use quite a bit in examples and homework problems. The ideal gas law, this one doesn't fall into the A, B, C, D range. We'll look at the D gas law in a little while. But the ideal gas law kind of combines all of these gas laws that we've talked about earlier, and gives us a constant that we're going to call R that will relate all of these numbers. Now, this particular constant, R, is only going to work here if it cancels with the units that are used in the rest of this. And that will work fine if we use moles here and Kelvin here. And for pressure, we'd have to use pascals, which chemists don't like to use quite as much as physicists do. And for volume, we'd have to use cubic meters, which again, chemists don't care for as much as physicists do. So instead, we like to use a different R. These two R's have exactly the same meaning. It's like saying 1 gallon or 128 ounces. It's exactly the same thing, but in different units. And we'll use this R, 0.082058 or 0.08206. You don't have to memorize these, by the way. They'll be given on the test with their appropriate units. But this way we can use liters for volume, atmosphere for pressure, moles for amount, Kelvin for temperature, and have all of our units still cancel correctly. And we're going to work out some examples on this in class when we meet. All right, that's a good pausing point. I think we'll stop there and move on to Dalton's law in the next video.